Hi, everyone, and thanks for joining this afternoon's webinar. Our webinar topic is Business Intelligence and Evidence-Based Decision Making. My name is Mahdi Iskandari. I'm Program Manager with McMaster Continuing Education, and I'm very pleased to co-host today's session and to welcome my colleague, Jim Green. Before we start, I would like to acknowledge and recognize that McMaster Continuing Education is located on the traditional territories of Mississauga and Haudenosaunee nations and within the lands protected by the Dish with One Spoon Agreement. Now, I'm going to hand it over to my colleague, Jim, to start the presentation.
Hello, everybody. Thanks for your time today. My name is Jim Green. I'm the instructor for the DAT Business Analytics course here at McMaster Continuing Ed. I do apologize for my voice. I've got a bit of a bug. One of the highest profile topics over the last 10 years or so has been the concept of evidence-based decision-making. It's a bit of an unfortunate phrase because it implies that prior to the early 2000s, a dartboard was the most used device to determine an organization's next steps. What it really refers to, though, is the enhanced use of data and the ability to extract the information contained within using a variety of techniques. So it's those techniques that we're going to talk about for the next 45 minutes or so. Here's the definition of business analytics. It's kind of a catch-all term for those techniques and sources that are frequently used to guide the organization to its objectives. As you see, it includes a variety of elements: statistics, IT, data science, a number of others, but there's also a significant focus on communications, especially through visualization. Pictures are worth 1,000 words after all. The point here is that you can do the best, most incisive analysis, but if it can't be put into play by the business or the organization, it's useless. So with that, here are the topics we're going to take a look at this afternoon. With only 45 to 50 minutes, we can't go into these topics in detail, but we can provide an overview, which I hope will pique your interest and lead you to investigate further. There we go. So we're going to start at the beginning with an explanation of data and information, a discussion of classical probability and modeling. Two key topics, forecasting and risk analysis, follow, and these are both integral to any kind of planning that you do, whether personal, for the organization, or anything else. With the right tools and sufficient data, organizations can develop a path to optimization, ensuring that all available resources are used to their utmost. And then finally, we're going to look at the decision process itself and lay out the process which will enable the most rational decisions, which will benefit the organizations most. So, data. There is a big difference between facts and data. Data are, by the way, data is a plural. Datum is singular. It's a pet peeve of mine, sorry. But data are collected through some kind of measurement process: sales figures, employee turnover, COVID-19 rates, and many, many others. Of course, you have many examples yourself. The key point here is that the data are organized, or can be organized in some way, whether in a simple spreadsheet using Excel or a more complex data warehouse or data lake. So the data really are just the raw materials. When we apply the tools and techniques, we come away with the information that's contained within the database. It's a bit like a sculptor seeing the form of the art within the block of stone and then paring away the unnecessary materials until he's left, or she's left with the final product. Before we continue on, there is one topic I'd like to address just briefly, and that is the idea of big data. Big data was a buzzword about 10 years ago. It was a very hot topic, and theoretically, it was going to be the solution to all of our problems. I've heard that before, right? New tools like R, Python, Hadoop, and many others were developed to handle the massive amounts of data coming from the internet, coming from other sources, all available online to just about anyone. And with tools easily available, many of them free, the idea of big data was very attractive in terms of being able to pull out all the information necessary to make the right decisions. Okay. And to a fairly large extent, that's come to be true. But the point here really is that big data, in and of itself, are still just data. until the information contained within become available, big data is not really that helpful. The overall concept is really no different from any other kind of analysis. It's just been surrounded by a lot of hype. Now, the hype has calmed down a bit, and big data is part of mainstream analysis. And again, there are quite a number of tools that have been developed and are being developed to process big data even more efficiently. So with that little segue out of the way, let's take a look at our next topics, modeling and then probability. Excuse me. I think we all know what a model is. It's a simplified, sometimes idealized representation of reality that mimics the key components we want to investigate. We can't include everything, but we can include those things that are most important to the investigation at hand. So by its nature, it doesn't include everything, but it does include the things that the analyst needs to obtain the objective, whether it's to forecast sales, to determine the requirements for ICU beds, to determine the best location for a new government office, and many other things. So there's several kinds of model, ranging from the very simplistic to the very highly sophisticated, which would include things like AI simulation and machine learning. But here's a few examples. Okay, there's three types of model. We have a verbal description, which is simply a description of what's going to happen. Sales start slowly, increase as word gets out, and then slows as the market reaches saturation. There's a visual example here, a graphical representation, and then finally there's a mathematical formulaic representation. So all three of these examples show essentially the same thing, a fairly typical adoption of a new product in a new market. Which one provides the most information? Well, if you're an analyst, you might immediately understand the bottom one, the formulaic one, but for most of us, the graphical example is the most useful. So what's the purpose of a model? Well, there's three main functions. The first is descriptive. It explains the current situation and provides information for things like what if scenarios. What if our sales increase by 5%? What if our costs increase, and so on. So that's a descriptive model. The second kind is a predictive model. It focuses on what will happen in the future. So many predictive models are developed by analyzing historical data and assuming that the past is representative of the future. And in many cases, that can be the case. That can be true. But if you think back a few years ago and what the economy looked like in 2019, and then look at the changes that took place due to COVID, the pandemic in 2020 and 2021, there's a significant break in historical data at that point. So we have to be cautious when we're looking at predictive models. The third kind is prescriptive, and that is a model that helps decision makers identify the best solution to a problem or opportunity. And here we have the concept of optimization, where we're finding values, decision variables that minimize or maximize something. So it could be reducing cost as much as possible, given certain constraints, could be increasing profit, or it could be just maximizing efficiency in a manufacturing process or things like that. With that, let's take a look at probability. One of the things that models imply, of course, and we talked about this, is that there's a certain amount of uncertainty whenever we use a model. There is a tendency to take the results of a model as fact, which is not necessarily the case. There's always a certain amount of change inherent in any model when you apply reality. So we use probability to determine the likelihood of events taking place. And this is actually one of my favorite topics. As I mentioned, life is full of uncertainty. We can really only examine the likelihood of something happening or not, from anything from getting on the bus to the success of a new product. Probability theory provides some guidelines that'll help us to go beyond subjective experience-based chances and to a much more rigorous quantitative-based process. Okay, and again, things seem to happen in threes here. There are three types of probability. There's classical, relative frequency, and subjective. So again, excuse me, classical probability is very frequently illustrated with dice rolls. It's a relatively straightforward calculation. All we do is determine the likelihood of rolling a certain number based on the total number of possibilities and how many combination of two dice rolls result in the number. So for example, if you roll two dice, 7 is the most likely sum that you're going to get, right? Because you can have a 1 and a 6, a 2 and a 5, 3 and a 4, or the reverse. So there are 6 opportunities to roll a 7 out of 36 possible rolls, right? Relative frequency probabilities are based on empirical data. By looking at previous history of sales of healthcare data, other historical information, we can say that with some reasonable confidence that a certain event is likely to happen. There's going to be a certain outcome. The third kind, subjective probability, is based on experience. Poker players typically can review the cards in their hand and can essentially rank the likelihood of their winning based on what they've seen before. So, okay, now that you're ready to hit the casino, how is probability used? Okay, let's take a look at an example from the airline industry. When should an airline discount ticket prices? Okay, this is something that comes up on a regular basis with perishable goods like airplane seats. So here's an example. We've all seen the price of airline tickets rise and fall, mainly rise, but there are times when airlines offer discounts to get what are called bums in seats rather than lose all of the revenue for an empty seat. So here's a calculation that illustrates how this could occur. The regular cost of a ticket is $560, but the airline will drop it to $400 if it looks like sales are slow. Based on some criteria, perhaps historical data, intuition, or maybe even the dartboard we mentioned earlier, the company calculates a 75% chance that all tickets are going to sell at full price. Based on this, the expected value of a full fare ticket is $420, okay? And you can see that the expected value is equal to the price of the full fare times the probability of selling a full fare ticket, which is 0.75 in this case, plus the price of a discounted fare. So when we look at the arithmetic, it's 560 times 0.75, 75%, plus $400 times 0.25, okay? The probability of selling a ticket either at full price or at a discount is equal to 1. So if it's 75% likely that we're going to sell a full fare ticket, then the probability of selling a discount ticket is the remainder, 0.25. So our expected value is $420. Okay, so far? Based on this expected value, because the discounted price is lower than the expected value of selling a full fare ticket, the airline should not discount the tickets, okay? They are going to make more money by selling full fare tickets, even with a probability of 75%. Okay, so that's how probability can be used in the airline industry or anywhere where we have perishable goods like airline seats, okay, or theater tickets, for example, other things like that. So again, this ties in pretty nicely with our next topic, forecasting, because of course, what we're doing with probability is we're trying to determine what's going to happen in the future based on what's happened in the past. So our next topic is forecasting. And once again, we have something that we do on an ongoing basis, on an almost daily basis, from a monthly budget to how much to take out at the ATM. Organizations use several different techniques of varying sophistication in terms of forecasting. So the three major types that we have here are qualitative and judgmental techniques, statistical time series models, and explanatory or causal models. We look at qualitative or subjective. We have something called the Delphi method, which has been around for quite a long time. The Delphi method is actually named after the Greek oracle of Delphi, which provided auguries of the future based on getting answers from the god Apollo through a high priestess. We don't do that anymore. It's gone into, there's a certain lack of confidence, let's put it that way. The modern Delphi method doesn't involve gods, but a panel of experts. By sharing several rounds of opinion, this panel of experts will eventually reach a consensus based on a specific set of facts. So Delphi is highly subjective, even though a number of experts are consulted. It's really only used if there are no data available or if they're of poor quality. Sometimes, too, it's used for very long-range forecasts, what's likely to happen over the next 20 years, something like that. More typically, though, when data are available, our organizations will use historical figures to develop a trend line. Okay, and this is our second type. Time series forecasts. Okay, it's called time series forecasting, and it's very frequently used when conditions are likely to be reasonably stable. Some elements like seasonality, for example, cyclical effects, and trends can be included in a forecast as well. Trends show an upward or downward movement of the data based on incremental changes. Trends are not typically enough to change the overall pattern, but they can account for some little bumps in the road, to call them that. Seasonality is definitely an important aspect of forecasting as well. Retailers change out their inventory based on the time of the year, of course. Right now, for example, it's pretty hard to find a parka in clothing stores. Retailers are stocking bathing suits and shorts, getting ready for spring and summer. Forecasters recognize this and incorporate some seasonality in their models. So again, you can see what's happening here. This is a chart of birth rate in the United States from 1950 to 2010. And you see that the birth rates are dropping quite dramatically, particularly through the 70s, 80s, and even into 1990. Again, if we were to continue on and look at 2020 as the next data point, where would it likely be? Be fairly close to where 2010 is, around 1.5, maybe a little bit lower, maybe a little bit higher. But you can see how visualizing a trend line like this can make forecasting a relatively straightforward thing. The third kind of forecasting uses explanatory or causal models as well, or causal variables, pardon me. So we can add in a causal factor, as in this example. This is a graph of gallons of gasoline sold over a period of 10 weeks. And then in the 11th week, we're going to try and predict how many gallons are likely to be sold. But instead of having a simple trend line, we now have an additional factor at play, and that is the price of gasoline. Okay, as you see, it varies from $3.95 to a high of $4.20, it looks like. And then it bounces up and down a little bit, okay? So certain elements of this forecast are fixed. Like there's the amount of gas you have to commute to work. But we do recognize here that some car travel is discretionary and is dependent on, gas prices. As prices increase, there are fewer recreational kilometers that are logged. Okay, so this is a causal variable. Now, whenever we look at forecasts, we recognize it's a construct. We recognize it's never going to match reality exactly. There's always an inherent element of risk in forecasting. And in fact, with any decision or any modeling process, and that's our next topic, we're going to look at risk. And again, we talked a little bit about casinos before. Risk assessment is quite frequently determined using something called the Monte Carlo simulation. Monte Carlo simulations are algorithms used to measure risk and to understand the impact of risk and uncertainty in various forecasting models, particularly with finance and with project management in terms of use of time and so on. They model outcome probabilities, give you an idea of what can happen and how likely a certain outcome is based on a number of different inputs. In addition, this is a simulation that allows you to create graphics based on the data. It can help you find the scenarios that produce a certain outcome. So again, looking at this, we talked about dice rolls a bit earlier. This is the probability density, as it's called, of rolling certain numbers with the sum of certain numbers with two dice. And as we talked about before, 7 is the most likely outcome of rolling 2 dice in any event. And then you see the relative likelihood of rolling a 2, a 12, or any other number here represented graphically. Okay. And again, if you look at the title of this chart, you see that they've actually rolled the dice 1,000 times, okay, simulation, and come away with this rather nicely balanced chart here. So the simulation really involves creating models with different values input to determine the risk analysis. You substitute a number of different values in any scenario that includes a level of uncertainty. And then depending on the number of possibilities, the simulation produces results you can calculate over and over using different values at random. This means that the kind of simulation can involve thousands of calculations before it actually achieves a result. One of the things that my former employer used to do is develop models based on Monte Carlo simulations, and it was not uncommon to run 10,000 simulations to determine what was the most likely outcome given certain variables. Okay. So risk is inherent in just about everything we do. We want to minimize risk whenever we can, right? On the other hand, we do want to get the most out of the resources that we have. So this involves the process of optimization, our next topic. Goods and services are usually created with a number of limited inputs, right? You have a certain amount of time, you have a certain amount of money, you have a certain amount of resources. So processes are constrained by things like labor hours and so on. Optimization helps analysts find the best use of these limited resources to get the most out of what we have. As you see from this visual, there are a number of solutions that will work for this manufacturing process, but there's really only one optimal solution where resources are used to their best effect. And again, if we look at the chart here, we see that there are certain constraints. There's a certain number of fabrication hours that can be used. There's a certain number of finishing hours, which is the green line here. And because there are a couple of different products being manufactured, we have to have a certain number of each in order to meet, let's say, a contractual agreement. So within that, we have that area, the sort of pinkish triangle called the feasible region. So anywhere within this triangle, within the feasible region, we can meet our various constraints and manufacture these products effectively. But really, to get to the max, to get to the optimal solution, we want to operate so that we're at the corner of the triangle there that's circled. That's the optimal solution, where we're using all of the resources as effectively and efficiently as we possibly can. Okay. So far, we've talked about a variety of topics. We've talked about modeling, forecasting, probability, risk, optimization. Our last topic is decision analysis itself, where we can actually map out the key elements of the decision itself. This is an example of a decision to either expand a facility or to do nothing, okay? At each point, called a node, something happens, either a decision or an input of some kind, which leads to a result. In this case, the decision points in green are associated with a probability either of economic expansion or contraction. And as you see, it's a relatively straightforward approach here. We said it's either it's a 50-50 expansion or contraction. So the branches lead to possible outcomes based on the decision taken or in the change in circumstances. Each node represents an option. Each sub-decision leads to the final decision. So every step can be approached as a probability, and the outcomes can be predicted based on whatever criteria you have. So this is our very brief overview of business analytics. I hope it's piqued your interest. You can take a look, or sorry, I can suggest you take a look at the data science program offered by MCE. As you see, there's 3 streams that you can follow. For more information, you can visit our website. Maddie, I'll hand things over to you, and you can discuss this in a little more detail.
Okay, thank you so much, Jim. I'm going to give you a high-level overview of the program we have at McMaster Continuing Education. So just a little bit of background about our program. We have a unique 3-stream type program. We launched this program in 2017 in partnership with MacData and McMaster Business School. And after that, the program, after a few years, evolved from big data analytic into 3 separate streams. You can see on the screen here, a basic level, a data analytic program, and intermediate level, and somewhat experienced level, data science and big data programming architecture certificate. And we did this in order to meet the training need and different type of interest from our audience. And well, I can say, like, in each of these program streams, we have multiple course options. So we have a level of flexibility if you want to take maybe 5 courses to do a certificate in each of these streams, or maybe move between the streams. Or if you're familiar with some of the topics, we have a shorter format of the program. We call it Certificate of Professional Learning. And there is definitely an option if you want to take one of courses just to catch up with like emerging topic in data and analytics. That's another option. Our instructors are professional in the field of data. They have a different background. Some of them are working in finance, retail, consulting, and many other areas. And this actually brings in rich type of input from their work experience they can share with our students, and many different tools exposure for our students. So that segues into the other point we have unique about our program, which is the hands-on piece. So we have a balanced form of concept and hands-on in each of these 3 streams. In data science, for example, we have a capstone course, and we have a small project throughout the other courses as well. So we are focusing on a balance of concept and hands-on experience. We have our courses scheduled in a part-time study format, and they're running on evenings and weekends just to give another layer of flexibility for our students. And most of our courses are running in a virtual live format. So with that, I want to thank you again for joining our session today. We hope you found this session useful and informative, and you enjoyed the session. I'd like to take this opportunity to share with you that the spring enrollment is open, and we welcome you to check out a few of our courses that are still available. For example, you can check our business intelligence course, which is the course Jim was talking about in this session. And we have open source intelligence courses lined up, and they're scheduled to start on May 28th and June 1st. And the second OSI course is actually a continuous enrollment format, so you can start anytime after June 1st. And well, if you have any type of program related question, feel free to put it in the chat during this session. After this session, do not hesitate to reach out. We are available via the contact us form. You can see the information about contact us form, and via the program email, bigdata@mcmaster.ca. Thanks again. We look forward to connecting with you soon.